The other day I asked my son, if I roll a dice, what are the chances of, say, I can't remember what it was, but a 6 coming up? And he said, of course, the answer is 1 in 6. And then I said, well, what if I had 2 dice and I roll the dice? What are the possible numbers that can come up? And he said fairly quickly, I can get like a total of 2, 3, 4, 5, all the way through to a max of 12. And I said, what are the chances of those coming up? And he said, well, the chance is going to be the same for all of the numbers. And of course it isn't. It isn't the case. And if I gave you $100 and I said, put it on a number that you think will come up, everyone in this year level should bet on 7. Okay, that's the number that you should bet on. Now, why? Well, what we've got is multiple events when we roll 2 dice. Okay, multiple events occur when 2 or more events occur in sequence. That is, one event occurs after another is completed. Now, I know we're rolling the dice at the same time, but it could be at a different time. Like I roll 1 dice and then I roll the other dice subsequently. So we do consider them 2 events, even though the rolls are occurring at the same time. And what we've got here is a table. Okay, it's often called a lattice diagram. Okay, so if you hear it called a lattice diagram, that's what this thing is here. And what we do is we represent 2 events in these tables. Now that's the best we can do these tables is 2 events. We can't represent 3 events. We have to use some other form to display the possible outcomes. All right, now let's see what it would say then about this and why the answer is 7 and why you should put your money on 7 coming up. Well, if you have a look at it, the way we can get 7 is via a 6 and a 1, a 5 and a 2, a 4 and a 3, a 3 and a 4, a 2 and a 5, and a 1 and a 6. There's 6 possible ways out of 6 times 6 is 36 equals 1 in 6. And that's the best chance of any number. You can see that there's 6 possibilities or 6 ways that 7 can be made. There's only 5 ways 8 could be made. There's only 4 ways that 9 can be made. 3 for 10, etc., etc. The worst ones to bet on are obviously the 6 and the 6 and the 1 and the 1, or 12 and 2. Okay, so he was in fact wrong. Okay, that each of these don't have an even chance, even though when I roll the dice, the chance of a 1 coming up is 1 in 6, 2 coming up is 1 in 6, etc., etc. All right, so what we've got is a sample space here of 36 elements, and what we want to do is find the probability of getting a 1 first and a 5 second. Now that's that exact event. So a dice has 1 first and then a 5 second. Well, where is that event? There it is there. There's only one perfect match for that, and that is 1 over 36. All right, the probability of getting a double. Well, a double is the same number. So what we've got is a 1 and 1, 2 and a 2, 3 and a 3, 4, 4, 5, 5, 6, 6. So that's 6 events in 36. That's a 1 in 6 chance. Sum of at least 10. Now remember, at least means 10 is the smallest acceptable value. And if you're debating this in your mind, think about it in terms of money. If I said you must pay me at least $10 for teaching you this year, then if you wanted to give me the minimum amount because you didn't think I did a good job or whatever, you'd go, well, if I have to give him at least $10, I'm just going to give him a tenner. Okay, so that's what I think about when I think about at least, is what is the fewest or the smallest acceptable value. That would be 10 would actually meet the requirements of this. So it's 10 or more. So here is the 10s, that's those ones. Here is the 11s and here is the 12s. Now note that if we count them up, we've got 3, 2 and 1. That's a total of 6 possible outcomes that produce at least 10, and that's 6 out of 36, 1 in 6 chance of getting at least 10. Sum not equal to 7. Okay, so that'd be sum equal to 2, 3, 4, 5, 6, 9, or 8, 9, 10, 11, 12. Now that's a lot of counting, but here's what I'm going to do. I'm going to say that it's equal to 1 takeaway, so not equal to 7. I'm going to work out how many ways there are to do 7. We talked about that earlier. There's 6 ways. That's 1 takeaway, 6 out of 36. So basically what I'm going to do is actually, so sum not equal to 7, I'm going to get the sum or the number of instances equal to 7 and remove it from the total probability, which is 1. And what that will give me is the sum not equaling 7. That is equal to 7. So if I remove it from 1, I get not equal to 7. Much easier than counting all the single elements. All right, so 1 is 36 on 36, take away 6 on 36, which is 30 on 36. What's that? It's 15 on, what's that, 18? Yeah, which is equal to 5 on 6, I believe. Yeah, okay. All right. So what we can have is this thing called with replacement and without replacement. And I've often played this game in year 7. I didn't have any of you guys in year 7 because I spent a year at another school and very quickly came back. Play this game with year 7s and let's just say that this is a club, diamond, a spade, and a heart. And what you do is you put one of these like symbols in each corner of the room. And what you do is you get the students to go into a corner of the room or choose one of the corners. So they choose club, diamond, spade, and heart. Now the game works such that you have a deck of cards, and what you do is you pull out one of the cards, and say you pulled out a club. What would happen is, depending on how you want to structure the game, anyone who is standing at clubs stays in, or anyone standing at clubs goes out. I don't know, it depends on what you want to do. All right, and so what happens is you do that, and then let's just say that anyone standing at clubs goes out, right? Then what the students do is, so all the girls who were at clubs sit down and the remaining students distribute themselves across the 4 again. Now, I can always pick up an interesting, like a kid who gets mathematics and who gets number, when she asks me, are you going to put the card back in or are you going to keep the card out? Okay. Now, why is she asking that? Well, if I drew a club out, remember that there's 52 cards in a deck, all right? So if I draw a club out, what that means is after one instance of this happening, I've got a 12 in 51 chance of getting a club. Diamonds, I've got a 13 in 51 chance. Spades, I've got a 13 in 51 chance. And hearts, I've got a 13 in 51 chance. Okay, so you notice here that these here, 13 out of 51, they have a higher chance of being picked out. Now, it's not huge, okay? It's like not saying this game is now heavily stacked, okay? But what it's saying is that kid is really thinking about it, because if I don't replace the card, then she should stand at one of diamonds, hearts, or spades. She should go to one of those ones. She should not go back to club. All right, if it's with replacement, that is I put the card back in, then there's no question. And what you should do is just distribute yourself randomly, because each of these has a 1 in 4 chance of actually being selected. All right, so let's explore this. So replacement, and this is an example, selecting a card out of a pack, replacing it, selecting a second card, and then replacing it, and then a third card. There's always 52 cards in the deck. Non-replacement is selecting the card out of the deck and then like canning it, putting it aside or something like that. So we select a third, then a second, then a third. So originally there was 52, then there's 51, then there's 50. All right, so let's just think about what we've got here. So we've got 2 selections are made from the digits 1, 2, and 3. So just say we've got like 3 tiles in a bag, 1, 2, 3, right? And we've got this with replacement situation. So I could select tile 1 and then I chuck it back in the bag and I can select it again, okay, because it's always been replaced. Now I can select 1, then a 2, a 1, then a 3. So notice that with each of these ones here, I can select the same one again because it goes in there. Now have a look at the difference in this table here. So this is the with replacement table and this is the without replacement table. Right, so the event 1, 1 is deemed not possible in this table here without replacement. And the reason for that is if I dip into the bag and grab the 1, it's gone. Okay, so that when I dip into the bag again and I go, ooh, I wonder whether I'm going to get a 1, there's no chance of that happening because 1 is not in the bag. Okay, so you're only either going to get a 2 or a 3. But these events are not possible because the first pick means that I've grabbed it and it means it's no longer there to be picked for a second time. So it's very important to read these questions and work out whether it's being replaced or not. All right. So event A is tossing a coin twice. Now this is implied replacement. Okay, so even though it says it doesn't say with replacement in the question itself, although I know the heading is with replacement, it's implied because when you toss a coin, you can't take away the head. Like the coin is a coin. You can't sort of grab the coin for a second time and go, yeah, what is it now? Now that I've taken heads out of the coin, like the coin's got a head and a tail at all times. Right, so it's implied. Don't wait for it to be said. Like, don't be sticking your hand up in a test or an exam and go, oh, is it with replacement or without? Because you don't say it. Okay, it's implied. All right, anyway, let's get stuck into it. So this is what we're going to call toss 1, which can be either head or a tail. And this is going to be toss 2. And this is going to be a head or a tail. Now, what can happen is I can get a head and a head. I can get a head and a tail. I can get a tail and a head. And I can get a tail and a tail. All right, so this is now my sample space. So the sample space is going to look as follows. I can get head, head, that's one of the things I can get. I can get head, tail, I can get tail, head, and I can get tail, tail. These are the possible things that can happen. List the possible total outcomes for A using set notation. Well, that's just what I've done there. Yeah. Oh, so yeah, I've done the lattice diagram to do it, and then this is what the set notation would look like. All right, find the number of elements in A. Okay, so the total possible outcomes. The number of elements in A is 4. All right, what are my chances of getting a head followed by a head, or head and a head? Well, I've got a 1 in total of 4 outcomes here. All right. So head and tail, that's head and tail. That's this particular one here. All right, so that's going to be a 1 in 4 chance. Now this is also an interesting case because probability of head and tail is equal to, or it's the same as the probability of a tail and a head. All right, and so in that case, if we know that the head and the tail is a quarter and the tail and the head is a quarter, in fact, this particular event here has actually a quarter plus a quarter. Okay, so quarter plus a quarter is equal to 2 quarters, which is equal to a half. So head and tail actually is not a 1 in 4 chance, even though it looks like head and tail is that, because of the way this is written, head and tail. Okay, so in fact, this is 2 quarters or a half. Right, this one here, we've got tail and tail not. Okay, so that means we don't want this one. We want everything else, which is all of these. So it's 3 out of 4. All right, getting a little tricky with this one here, but see if you can do this one or handle it anyway. Find the probability of getting 2 heads, given that the result of the first test was a head. All right, so what we actually know here is that the first one was a head. So I know that these 2 cases match it, okay? That means that case there and that case there are not even worth considering. Means that we've got a total of 2 possible outcomes we can consider. So notice that what we've done here is we've actually ruled out that and that from the sample space. They can't happen. All right, that's not what we're interested in because you've been told that the first test or the first toss in this case was a head. So what I know is head and head is 1. There's 1 possible case out of the 2. So the probability of two heads, given that given the result of the first test was a head, is actually a 1 in 2 chance. All right, here's an example of without replacement. So 2 letters are chosen from the word kick without replacement. Right, so K, I, C, K are the possibilities for, let's call it pick 1 and pick 2. K, I, C, K. All right, now let's kind of rule this up a little bit so we can see the outcomes a bit better. All right, K, I, C, K. All right, so what happens is I've grabbed this particular K here on the first pick, which means I can't grab this particular K again. I know that there's another K here, but we're talking about one in particular. This other K is represented by this one here. So in fact, this K and K event can't happen. It can't be done. All right, I can pick the K and then the I. That's acceptable. So KI would be an acceptable one. KC, I'm going to get. Now this is an interesting one here, KK. Now I said you couldn't do KK, but in fact you can do KK. You can pick the first K and then you can pick the last one. That event there is acceptable. So you really got to think about this. All right, and what you'll note here, see this, so I can do an I followed by a K, that's for sure. An I and an I, can't pick an I and then the same I. So that's not going to happen. And what you'll note here is across what we call the leading diagonal here, we're going to get crosses all the way through those. None of those events can actually happen. I can get an I followed by a, what's that, a C, an I followed by a K. I can get a C followed by a K. I can get a C followed by an I. I can't get a C and a C because I've already grabbed it the first time around. And I can get a C followed by a K. All right, the last one. Now, I can get this last K and the first K. That's an acceptable event. What I can't do is grab the last one and then grab the last one again because I'm not replacing it. K followed by an I and K followed by a C. All right, find the probability of obtaining the outcome KC. There's one. And there's one. All right. So that's going to be a 2 in 3, 6, 9, 12, 1 in 6 chance. Selecting 2 Ks. KK, KK. 2 in 12, 1 in 6. Selecting a K and a C. Okay, so that's probability of K and C. All right, so this is something very specific here. K and C is the same as the probability of C and K. All right, so what we're looking for, we've got a KC and a KC. Now we've got a CK and a CK. All right, so now we've got 4 of these. So 4 of a possible 12, 1 in 3 chance. Selecting 2 Ks, so getting KK, given that at least 1 K is selected. All right, so it's either this row here or it's this row here. So a K has been selected first. So it could be this particular K or it could be this particular K. In which case, there's 6 possible outcomes because these ones here are now not relevant to us. All right, so K has been selected first and KK, this one here, represents 1, or this one could have been done, in which case we get a KK here. A 2 in 6 chance or a 1 in 3 chance. So basically, if you told me at least 1 K has been selected, okay, what are my chances of getting 2 Ks? I know that that's a 1 in 3 chance because there's 6 possible outcomes of this particular scenario where K has been selected first, of which KK is 2 of those 6 possibles. All right. Now, sometimes the replacement, girls, is also implied. And I remember a question a few years ago in a Year 9 exam, and what it involved was was something like this. It was like Mr. Tench bought the maths department some donuts, different colours or flavours or whatever it was. And what happened was Ms. Abby chose one of the donuts at random and consumed it. Okay. Now, the question didn't say at any point she selected a donut without replacement, but we presume, girls, without going into the gory details, that once a donut has been consumed, it cannot be replaced. Okay, so read the question carefully and don't just assume that if it doesn't mention without replacement, that it's being replaced. Okay, you need to think about it. You need to imagine the case. All right, so here's the set work 8E questions 3 to 11.